All right, so we're going back to some good old Java development, and we're back to working on the command line, despite having set up Eclipse, where you're setting up Eclipse for future use. But for today, we'll be back on the command line with VI. So I want to talk about linked lists today, and we learned all about linked lists in CSE 222, and the basic setup is we've got a series of nodes. And we can think of this node as having sort of two fields, a data field and a next field. And the next field is a pointer to another node. And so assuming that we have a handle to the list so we can get to the first node will point to a second node, which will point to a third node, which will point to a fourth node, and so on. And the last node will put a special pointer to null, which is our flag saying, hey, this doesn't actually point anywhere, which means that's the last node in the list. So that's our basic setup. And in 222, we generally used a sentinel node, a special node in the very beginning, whose purpose was to serve as the handle. And we wanted this handle to always exist, so we said, hey, we're going to treat this first node as not part of the actual list, just a handle to the actual first node. So if the list is empty, it looks like this. It's got a sentinel. If it's got one field, it looks like that, and so on. And part of why we did that was just because of the realities of how C handles pointers, and the fact that it doesn't have objects. But now that we've got objects and classes in Java, we can get rid of the sentinel node. And so I want to show an example of creating a class called a list node, which is going to contain these two fields, a data piece and a next piece. And this class will represent a linked list. So designing a class named list node, pretty easy. We make an integer field called data. So we can say class list node. And I'm just going to assume it's, a linked list of integers. So I'll say integer data. And then the next field is going to be what? Well, we're going to actually say the next field is just a list node. Next. And that's going to be our definition for a node of our list. And this is a little different from C, right? In C we had asterisks because we had pointers. We like to say we don't have pointers in Java, but we really do. We just don't talk about them. But when I say next is an object of type list node, it's really a reference to an object of type list node. So there's not an actual list node sitting inside this list node. There's a reference to another list node. So it's really like an arrow pointing to another box, and the next field of that points to another box, and so on. So we can build our whole linked list. We can make, add, search, print, delete methods, and all that kind of stuff built around these kinds of nodes. But that doesn't deal with the question of the sentinel node, right? We want to get rid of the sentinel. Sentinel was kind of a convenience in C. But we'd like to have actually, if our list is empty, we don't want any nodes. And if there's a single node in our list has one piece of data, and that's it. So we don't want to get rid of this special node in the beginning. So we're going to make another class around my list node, and I'm going to call it class myList. And inside that class, we're going to include a pointer to the first node of the list. And so we'll say something like, list node start. And start's going to be the actual first node of the list, or it's going to be null if the list is empty. But when we construct a myList, that's going to exist. We're going to have a myList. That's going to be our handle, the thing that we use to take hold of the list. And if we have an empty list, we've still got a myList. It's just going to happen to have a start that's null. And then when we add something to it, start will point to that first node, and so on. So that's our basic setup. Let's go ahead and hop into some code and actually make this work. So I'm in my class 7 area on the server under CSE 223, and let's make some classes. So let's start with a list node. So since I want the class to be called list node, it's got to be in listnode.java. Since it's a class name, it's got to begin with an uppercase letter, right? Not required by the language, but required by convention. And let's put some comments in here. So this implements a simple linked list of integers. And this will be wrapped inside a MyList class. That's just for future reference. All right, so what do? We say class list node. And we only really need 2 fields, integer data. That's the data stored in the node, and list node. This points to the next node, or null if end of list. That's all we need for a list node. Now we can add other things into here, but for starting purposes, that's pretty much all we need. So we'll leave that. And now let's make a mylist.java. Lots of typos. Alright, it's implementation of a linked list. Linked is comprised of list nodes. So again, it's in a file called mylist.java, so the class name is mylist. And we're not going to have a sentinel. But we do have a handle to the first node, so I'm going to say list node start. I'm going to set it equal to null. So that means the list is empty. All right, let's make a method for adding to the beginning of the list. All right, so we're going to insert into the beginning of the list. Let's write an add function. And if the list already has some nodes in it, what do we want to do? Well, we want to basically create a new node, have it point to start, and then change start to be that new node that we just inserted. And if our list is empty, if start equals null, then we want to create a new node, have it point to what the current value of start is, which will be null, and then change start to be that new node. So there's no edge case for a list being null anymore, right? Since we're inserting the beginning, we simply make a new node, point it to start, and then change start to be our new node. And we can do this because we're inside a class and we have access to this start node. So let's see what this looks like in code. So we'll add to the start of the list. So let's make a list node temp equals new list node. And we'll do temp.data equals the data that we're trying to add. And then we'll say temp.next equals start. So point to former head of list. Or, null if the list is empty to begin with. And then start equals temp. So this is the new head of the list. And we just return. That's our whole insert function. So let's print the list. So how are we going to print? Remember, our basic idea for traversing a list is to simply start at the first node, print its data value, follow its next field to another node, print its data value, follow to the next, print its data, follow to the next, print its data. And if following to the next takes us to null, then we're done. So we gotta be a little careful about, null pointer exceptions. But as long as we're a little bit cautious of that, it's not too bad. So let's do a list node temp equals start. And so this points to the start of the list. And we can just say, well, start is not null. And let's just print out, this is, well, temp is not null. Let's print out temp.data with a space afterwards. And then temp equals temp.next. And then when we're done, we'll just print out a new line just to, make all our output appear on one line, but with a separate line at the end. And that can be our print method. And that's our whole MyList class. All right. So I have not declared a constructor, so there's always a default constructor, which will, really do nothing except, create a list node and set it equal to null. So if I compile mylist.java, that should compile fine, and it also compiled list node into a list node.class. So that's all good. So let's make a main program. So let's test our list. So my list, list1 equals new mylist. And let's just add a few numbers to it. So we'll add a 3, a 5, a 7, an 11, and a 13. And then we can print it out by saying list1.print. So compile that. That compiles fine. Go ahead and run it, and we should see our numbers in reverse order because this is a FIFO, right? We inserted in the beginning, and we're printing from the beginning, so it comes out reversed. But, there's our linked list. And, I could also do mylist list2 equals new mylist. And I could do list2.add, and I could, put some different things in there. I could just put in even numbers. And I can print out list2 if I want. Well, we gotta say add. So go ahead and run that, and you can see we've got two completely independent linked lists. First one with prime numbers, second one with even numbers. No need to call an init method, no need to pass the name of the list to the add method. Why? Because the add method is being run as part of this class or as part of this class. So this does all the initialization that we need. And if we say list2.add, it adds to the list called list2. When we say list2.print, it runs the print method corresponding to list2. And how does that work? Well, because each time I create a list, I create a new start node, which is, part of that object, right? That structure, if you like, that we call list 1 or list 2 has its own object start, which is, the first node of that particular list. And so so we have truly independent lists, and we can make as many of them as we want, and they don't conflict with one another, and so on and so forth. So that's a nice sort of short, contained example of how we build up a data structure by hand. Now, we already know about the linked list class that comes with Java under Java util, but this is an example of how we can use our 222 understanding of data structures and build up these data structures ourselves. All right, so in the problem set, you'll explore this yourself. You'll start off by recreating some of the work that we just did, making those two classes and add in a print method. And, as usual, rather than freezing the video and copying the code verbatim, it's more useful if you kind of think about what happened in the video and make some notes describing, how things were done, and then working from those notes and from your understanding, try to recreate this work. And, it shouldn't come out looking the same as what I just did. It should be your own version of it, but it should behave the same. So that's the benefit of these first few exercises. And then instead of printing the contents, see if you can make a method that makes a string containing the contents. In other words, make your same loop that goes through each node, but instead of printing the contents of the data field, append it to a running string and put that in something called public string toString. And now you should be able to examine the value of a list from your main program by simply, concatenating it to a string and printing it. Then go ahead, write a search method, write a delete method. Delete, remember, if you delete the first node, that's going to change what start is. So you've got an edge case there to deal with. And then go ahead and change your add method to insert in a way so that the list is always sorted. So similar to the second version of linked lists we did in 222. All right, we'll do the same thing for trees in the next class.